Hello everybody, and welcome to the beginning of page 137 in the workbook. And on this page, we're going to be exploring a few more properties of orthogonal subsets of inner product spaces. Let's start with Theorem 6.3 here. So we're starting with an inner product space V and a set S of vectors that are orthogonal and non-zero. And remember, orthogonal just means that any two vectors in that set are orthogonal to each other. Okay, and we'll suppose that y is a vector that's in the span of S. Okay, and this theorem basically formalizes the observation that we made on the previous page. It gives us a way of writing y as a linear combination of the vectors in S. Okay, and that way of doing it involves inner products. Right, so y can be written as the sum, let's use I to n, not k to n. Okay, as I goes from 1 to n of the inner product of y with vi over the norm of vi squared times vi. And I'll make the comment, we actually proved this formula back in example 1 on the previous page. Okay, so we kind of already know this theorem from before. All right, and the theorem has a couple of useful corollaries to it, starting with corollary 1 here. So suppose that we have the same hypotheses that we did in 6.3, but in addition, we know that S is an orthonormal set. Okay, well, what did orthonormal mean again? Well, it just means that the vectors are orthogonal, just like they were up in Theorem 6.1, but they have an additional property that the length is 1. The length of every vector in S is 1. So if you think about that, in this expression here, all that would change is the fact that, well, actually it would still be true, but we could make one additional observation that if all of the vectors have length 1, then this norm of vi squared is just going to turn into a 1 in the denominator. And so the equation that we got in Theorem 6.3 is just going to simplify down to this. Okay, it's just a little simpler way of writing it if we add the hypothesis that our vectors have length 1. Okay, and then there's one other corollary that's very useful here. Okay, so corollary 2, we're assuming that we're in inner product space and we have an orthogonal subset. Okay, it turns out that if you have an orthogonal subset of non-zero vectors, you have a linearly independent set. Okay, and so I'd like to see if we can prove that. All right, so let's do that in the space that we have down here. Okay, so we'll assume all the hypotheses that we're given. What we want to prove here is that S is a linearly independent set. How do we do that? Okay, well, we need to show basically that if we take any finite set of vectors from S, okay, and form a linear combination that's equal to the zero vector, that the only way to do that is for it to be the trivial linear combination. Okay, so we'll start with a finite set of vectors here, v1 through vk and S. Okay, and we'll suppose that we have a linear combination of those vectors that's equal to the zero vector. All right, I'm going to be referring back to this equation, so we'll give it a name. Okay, so here's our linear combination, sum from 1 to k of ai times vi, which if we wrote it out would just look like this. a1 v1 plus a2 v2 and so on, up to ak vk. We'll assume that that's equal to the zero vector. Remember, in this chapter, we're using the notation 0v to emphasize that that's the zero vector. And what we need to show is that that linear combination is trivial. In other words, that all of the coefficients are 0. Okay, so let's remind ourselves of that. We want to show that aj equals 0 for all j. Okay, so let's see if we can do that. So we're going to kind of consider the coefficients one at a time. So consider any j between 1 and k. And then we're going to make an observation about that. Okay, so notice that the scalar 0 is the inner product of the 0 vector, 0v, with vj, that was one of our properties of an inner product. If you take the inner product of the 0 vector with anything, you get the 0 scalar. Okay, but then we notice that we have a way of writing the 0 vector from equation star. Okay, if you go up here, the 0 vector is equal to this summation, so we can make a substitution here. Instead of writing 0v, we can write that sum. Okay, so I'm just going to make a comment here that came from equation star above. Okay, and then we're going to use the linearity property of the inner product to take that summation and just move it to the outside here. So we can rewrite that as the sum from 1 to k of ai times the inner product of vi with vj. Does this look familiar? Okay, we did a proof very much like this on the previous page, back in example 1, I think it was. All right, we can make the same observation that we made there. Because the set S that we started with is orthogonal up here, we know that the inner product of vi with vj is equal to 0 whenever I is not equal to j. That's the orthogonality. Okay, so the only time that inner product is not going to be 0 is when we come to the jth term in our sum, when vi and vj are the same. Okay, so what that means then is we're just going to get one term from this sum, and it's going to look like aj times the inner product of vj with itself, which is the length of vj squared. Okay, same observation that we made back on the previous page. Okay, so if you look at the beginning and the end of this, what we've shown is that the scalar 0 is equal to aj times the length of vj squared. Where does that lead us? Okay, well, since we made the assumption that vj is not equal to the 0 vector, that means that this length here, the length of vj squared, is also not 0. So the fact then that aj times that non-zero length is equal to 0, we can just divide both sides by the length of vj squared, and that tells us that the scalar aj has to be 0. Okay, and that's what we wanted to show. Okay, if you look back up here, we wanted to show that each of those coefficients, aj is equal to 0, and we did that. J was arbitrary up here when we started. Okay, and so we have shown that indeed this set S is linearly independent. Okay, and we're done with the proof.